So the next speaker in today's afternoon session is R Venkatesh from ISC Bangalore. He will speak on graph polynomials from the algebras. And over to you, Venkatesh.
Thanks, Chandrasil. Yeah, so today I'll be telling you about some graph polynomial connections with Lie algebras. Okay, so I will actually begin with some background from the Lie algebras and then slowly get into what I'm interested in. So this talk is actually based on a joint work with Karthik Singh, who was a UG student here, who did his UG project with me. So okay, so because the result that I am interested in, okay, that I want to talk about, which involves too much technicalities, so maybe at the end I will spend some few minutes explaining that. But before that, I will tell you how this graph polynomials can be obtained from the algebras. Okay, so that I believe most of you will find it interesting. So to begin with, I will just recall the definition of Lie algebra. Okay, so what is Lie algebra? So it is a vector space over complex numbers which has some product, so that we usually denote it by this bracket. Okay, so that should satisfy these two properties. One is skew symmetric. So whenever you take a product xy, it should be equal to minus yx, and there is this Jacobi identity. So this is actually motivated from, like, if you take this vector space, finite dimensional vector space V, and then look at the endomorphism of V. Okay, so these are all linear C-linear maps from V to V, and that is an associative algebra. So the composition gives you product. So now what you can do, you can look at the commutator, so which is a bracket AB equal to AB minus BA. So that will give you Lie algebra structure there for that endomorphism of V. So more or less, the Lie algebra definition is motivated from that Lie structure that we study on that endomorphism of V. So one motivation to study Lie algebras, you can think this as like you are interested in understanding this associative algebra. So how far it is actually stay away from being commutative. So to understand that, it is enough to understand the Lie structure, that is that you get it from that commutator bracket AB equal to AB minus BA. Okay, so that's a small introduction. And as in the associative algebra case, you can also define what is called ideal inside G. So which is you take any elements x in I and y in G, then the product should be in I. So because of skew symmetric, we don't talk about right or left ideals. So all ideals are equal. Okay, and then once you have an ideal, you can talk about quotient algebra. So you take this G modulo I quotient space, and there is a natural product that is inherited from the G. Okay, that is given here. So now I will tell you what is the free object in this category of Lie algebras. So if you take some set X, then we know how to construct this free associative algebra generated by X. So what we can do, we can take all possible monomials that are coming from this alphabets X. So they are non-commutative monomials, and then take C span of that. Then juxtaposition will give you product on that associative algebra. Okay, so now what we can do, this you can take this associative algebra, define this Lie bracket as a commutator on this associative algebra, so which is given by this bracket AB equal to AB minus BA. So that will make this associative algebra, this free associative algebra, as Lie algebra. So to emphasize that Lie structure, we denote this bracket C this X just to emphasize the Lie algebra structure. So now you can see that this if you take if you consider this Lie algebra, okay, C bracket this Cx, which is the free algebra, so that will contain all possible monomials so that you can get it from X. Okay, but if you are interested in the free Lie algebra generated by X, then you don't need to take all monomials that is coming from this Cx. So then what you do, you simply take this FL of X by the Lie subalgebra generated by this X inside this Lie algebra. So that will be your free Lie algebra generated by X. So what is this FL of X? So this is just as in the associative case, you take all possible Lie monomials that are formed from this alphabets that are coming from X. Okay, so Lie monomials, as I told, it will be much more complicated. Okay, so because if you recall the definition of Lie algebra, it's highly non-commutative and non-associative algebra. Okay, so it satisfies that skew symmetric that makes it non-commutative, and there is this Jacobi identity which is actually highly non-associative. So that means so if you are interested in like computing some basis and so on, that becomes much harder if you compare with associative algebras. So we will see such examples in a minute. Okay, so but if you are looking at this free Lie algebra, so then what you are doing, you are taking all possible Lie monomials that are actually coming from this alphabets X. So the Lie monomials can be much more complicated. For example, if you take a bracket x1, x2, and then again bracket with x3, x4, so that will be very different from like other things. There is no associativity. Okay, so all possible funny Lie monomials can occur here. Okay, but here in this associative algebra, we understand all monomials. They are usual monomials. We have better understanding here. Okay. So now, yeah, let's move on. So what we are interested in, okay, so we want to associate some Lie algebra with given this graph G, okay. So for that, I will just fix this graph G, that is a finite simple connected graph. So I'm taking it to be connected for simplicity, okay. One can work with non-connected graphs, but that's okay. So the theory will be developed very similarly, but for simplicity, let's assume it is connected. So what I mean by simple graph, so it is a graph that doesn't have multiple edges or multiple edges or loops. Okay, I don't allow that. So that will be clear in a minute because I'll be interested in the vertex coloring. Okay, so that the vertex set of this graph G, we denote it by I, and the edge set by this capital E. So then what I do, given vertex, I associate one alphabet, I call it EA. Okay, these are all the alphabets I'm going to work with. So then what I do, I take a free Lie algebra generated by these alphabets EA, and then go modulo some relations. So what I mean by that, you take ideal generated by these relations. So what are the relations? The relations are also very easy. So you actually take the product, Lie product EA EJ 0 if I and J are not connected in the original graph E. Okay. So what is the meaning of this? It just if you think in terms of, okay, so whenever this Lie product is 0, we call that EA EJ commutes. Okay, using that language, what I'm saying, EA EJ, you let them commute if there is no edge between I and J. So that is a relation. Those are all the relations that I'm going modulo. Okay, so then it's clear what is the partially commutative Lie algebra that I'm interested in. So here is the definition. So the partially commutative Lie algebra associated with the graph G is nothing but you take this free Lie algebra generated by all these alphabets EI. So there is one alphabet for each vertex I. Okay, and then you go modulo this ideal I of G. So what is the meaning of that? What is that ideal generated by? It is generated by this commutator EI EJ whenever there is no edge between I and J. So the relations are, you allow EA EJ to commute if there is no edge between I and J. Okay, so if you take this partially commutative Lie algebra, then you want to actually ask many questions related to this. So this is one of the algebraic objects that one can naturally associate with this graph G. And of course, there are many other algebraic objects that one can associate. For example, so all those objects will appear here in this talk. Okay, so if you start from the monoid, okay, you can actually associate a partially commutative monoid, which is called Carpier-Forta monoid in the literature. And if you can also associate this partially commutative associative algebra. So you can take associative algebra freely generated by these variables ei, you can go modulo the relation, the same relation. You let ei, ej to commute if there is no edge between I and j. Okay, so that is one more object. Again, very similar to that, there are some groups also one can associate. Okay, they are called right-angled Artin group. So these are all some universal algebraic construction one can actually always do with this given graph G. And of course, one is interested in understanding the relationship between all these objects, the monoid group, associative algebra, this Lie algebra, and so on. So I will tell you like some of the relations in this talk, okay, and then I will tell you like why they are important. So let's look at this partially commutative Lie algebra. So this Lie algebra, it's naturally graded. So what is the grading that I'm going to do? So you fix a basis, this alpha 1, etc., alpha n, which is the standard basis of G power n. Okay. So then you take this Q plus to be the positive cone spanned by this alpha 1, etc., alpha n. So because only the elements of Q plus will appear in the grading. So what is the grading? So you assign this grade of EI to be alpha. That's it. Okay. So then the ideal that you have gone modulo, so that is bracket EI, EJ equal to 0, which is nothing but it is naturally, it's easy to see it's a graded ideal. Okay, there is no issue. So because of that, you will be getting natural grading here in this Lie algebra. So that will actually give you the graded decomposition. So that graded decomposition, I am denoting it by this. So the LG equal to direct sum G alpha, alpha in Q plus. So it's not very hard to prove using this Jacobi identity. So you can actually prove that this G alphas. So if you take alpha in Q plus and then look at this graded space G alpha, it is actually spanned by this very nice right-normed levers. So the levers of this form, this bracket EI1, bracket EI2, etc., bracket EIK minus 1 EIK. So they are called right-normed levers. And you can easily prove that these kind of right-norm levers, they will span this G alpha. Okay, and this is true for like any Lie algebra. Nothing special about this particular partially commutative Lie algebra. And what we are doing, of course, the grading should match. So the weight or the grade of this lever that should match with this alpha. So basically, what you are counting, what is the grading is all about? You are counting if alpha is equal to summation k alpha I. Then k is nothing but the number of EI that appears in this right norm lever. Okay, so that is your Ki. So it's a very easy grading. It just counts the number of EIs that appear in this lever. So which is very similar to the usual grading that we have it in the that partially commutative associative. Sorry, yeah, partially commutative associative algebra. So. So this grading actually kind of gives us some way of approaching this Lie algebra. So one can now ask there are many algebraic questions one can ask. So what can you say about these graded spaces? Okay, so can you actually give us the dimension of these graded spaces, which is very nice combinatorial problem. And from algebra point of view, can you give some nice basis of these graded spaces and so on? So you can ask so many questions. Of course, some of these questions are already answered for this free algebra case when the graph is complete. But for general cases, not much is known. Okay, for example, so if you take a G to be general graph, then we don't even know how to construct a right-normed Lie words basis for this partially commutative Lie algebra. Okay, so you can actually imagine like how it will be very hard to even say anything about this G alpha. Okay, because so you will be having like you are working with some algebra which is highly non-commutative and non-associative. So you have to handle with these Lie words, so which will become much more tricky. Okay, but combinatorially one will be able to actually compute the Hilbert series of this Lie algebra. So that I will tell you what it is. Okay, but before getting into that, I need some more notation. So let's move on. Yeah. So what I want to do, like given that graded decomposition, so we call this delta plus, which is those alpha in Q plus such that G alpha is non-zero. So which is a natural subset of Q plus that one can study. So they are called the set of roots of this LG. Okay. And the dimension of this G alpha, they are the root multiplicity. So you want to understand what is this delta plus and what are this dimension of G alpha. Okay. So those are the combinatorial data that one can associate with this partially commutative algebra, and you want to actually understand what they are. Okay. So can you tell anything about that? Of course, there is some very nice connection between these multiplicities and this delta plus. So that is given in terms of this denominator identity. So which says if you take this product side, the product 1 minus x power alpha power dimension G alpha, that will be equal to this sum side, which is somewhat very much easy to compute for given given graph G. Okay, so this is what is on the left side. This is nothing but multivariate independence polynomial. Okay, for each independent set S. So what is an independent set? It is a subset of a vertex set B, such that if you take a subgraph spanned by that set S, there should not be any edge between the vertices of S. So that means the subgraph that spanned by S is totally disconnected. Okay.
Sorry, the sum is over S an element of omega, right? Not subset.
The yes. Oh, sorry. It should be
Element. Okay.
Correct. Yeah.
Thanks.
So S is coming from. Yeah, S is an element in omega. Correct. So this is. You can see what I have done. Just I have taken some commuting variables. Okay. So because, like I said, one is interested in only this combinatorial data, dimension G alpha and alpha in delta plus. Okay. So to keep track of that, you can take just the commuting variables and then look at what is happening. So there is a very big background about this denominator identity. Okay, so if you know semi-simple Lie algebras and their generalizations, for example, Cosmodi algebras or Borch's Cosmodi algebras and so on, then you can see that this is actually a special case of Borch's Cosmodi Lie algebras denominator identity. Okay, we have a very general denominator identity that comes from the theory of Borch's Cosmodi algebras. So I will not get into that. Maybe I will actually outline one of the combinatorial proofs that one can give without getting into this Borch's Cosmodi algebra theory. So, okay, this equation is very, very powerful equation. You can see that there are some connections between this Lie algebras root multiplicities and independence polynomial of multivariate independence polynomial of this graph G. Okay, so once you stare at this identity, which is very powerful, one can actually do a lot with this identity. So let me actually give you some examples.
Sorry, 1 second. By the way, is the usual independence polynomial the determinant of any kind?
So the usual independence polynomial is one variable polynomial. You substitute all xi to be t.
I understand, but is it also does it have a determinant as representation? Like, is it a determinant of some kind?
Determinant of something?
I'm asking. I don't know. Yeah.
No, that yeah, that is not true.
Okay, thanks.
So yeah, I will come to that some determinantal version of some polynomials. Okay, if you take a matching polynomial of this.
That is this Gottsil-Gottman kind of
thing, yeah, matching polynomial of 3, that will be a determinant of that will be a characteristic polynomial of adjacent matrix.
Right.
Yeah, that question is very important in understanding this real rootedness properties. I will come to that in a minute. Okay, so you have this powerful identity. So by definition, I am allowing empty set and all singletons as part of this omega. Okay, so for example, if I take this part 4. This 1, 2, 3, 4 vertices, then you can easily see these are all the independent sets there. And the polynomial sum side is very easy to write down. Okay. Of course, this is very specific example, and then you can work a bit and then compute what is on the product side. that can be calculated for this example. I'm not giving any formula there, but you can sense in general it will be very, very difficult to compute. Okay. But using this formula, so I was actually motivated from the Lie algebra perspective. So all I'm interested in, I was interested in this computing this dimension of G alphas, the multiplicities. Okay. So the very first question, using this formula, can you give very explicit formula for this dimension of G alpha? Of course you can do. And then how explicit and then how useful that is. So I will tell you in a minute. Okay, so here is before proceeding, let me actually tell you the associative algebra connection. So I already told you now there is this natural associative algebra that can be defined for the given graph G. And there is a natural connection between that associative algebra and this partially commutative algebra. So what is that? So the connection is simply the universal enveloping algebra of that LG will be the natural associative algebra that you associate. Okay. So here is the definition of universal enveloping algebra. Okay. So what it says, it's actually a pair where LG is embedded inside this universal enveloping algebra. And given any Lie algebra homomorphism from LG to this associative algebra, which is treated as a Lie algebra with the Lie bracket AB equal to AB minus BA. So then this map F can be lifted to F bar so that this diagram commutes. Okay. So here again, like you can see, associative algebra and Lie algebra both are involved, and all this Lie homomorphism, associative algebra homomorphism involved. I have written as explicitly as possible. So this is the definition of universal enveloping algebra. You can prove that there exists universal enveloping algebra and it is unique up to isomorphism. And there is a very nice theorem that gives you, called the Pbw theorem, which gives you basis of this universal enveloping algebra in terms of the basis of this G, basis of this LG. Okay, so here is the connection, which is easy to prove once you use this universal property. The universal enveloping algebra of this LG is nothing but you take this free associative algebra generated by these variables EI, go modulo the obvious relation. You let EI, EJ to commute if there is no edge between I and J. Okay, and naturally this algebra is also graded because the ideal that you gone modulo is graded ideal. Okay. So then what we can do, once you have the grading, you can actually define this Hilbert series of this universal enveloping algebra. So the Hilbert series just keep tracks of the grading and the graded spaces, the dimension of the graded spaces. So which is given by this, the Hg of x bar is given by this, where x power alpha is product xi power k. Okay, where alpha equal to summation k alpha I. So then it's not very hard to prove using Pbw theorem. So there is this very close relationship between the Hilbert series of this universal enveloping algebra and the root multiplicities of this Lie algebra G. Okay. So what is it? So this is given this identity. So the Hilbert series of this universal enveloping algebra is nothing but 1 divided by the product set. Okay, so you can actually see that where the product is coming from. Okay, so now if you can compute this Hilbert series in some other way, then you can have that sum equal to product equality. Okay, so that is in some sense combinatorial proof of the denominator identity. So that can be done. That is actually done by Cartier and Sauter in their 1969 paper. And so Xavier Weyanot also used this heap theory language to prove the same result. Okay, so which basically both the results tells that, and there are some Lie algebra. Okay, the Lie algebra version is also available, but much later in 90s. But basically what it says, the Hilbert series of that universal enveloping algebra of this LG is given by 1 divided by the multivariate independence polynomial of the graph. So here also it should be belongs. Okay, yes, belongs to omega. So again, this proof of this actually one can do it very explicitly by giving some involution map on this universal elementary algebra. And then this can be found in this Xavier Vienna lecture series on Hibbs theory. Okay, that's where I have learned this proof. So basically, what you prove, you take this sum side product with this HG of x bar, you just prove that is equal to 1. Okay, so now clubbing together. So here this is coming for free from this Pbw theorem, and this is requires little bit of work. Then combining this together, you get denominator identity. Okay. So now, as I promised, okay, if you can actually look at that denominator identity and then ask what you can do with that. So one can do many things. Okay, we simply raise it power minus q and then see what happens. So what happens if you just raise it power minus q? So why I'm raising it power minus q? Because I want to think this as Hilbert series of this tensor product. So if you take this ULG tensor of q copies, okay, so then if you compute the Hilbert series of this will be the product of the individual Hilbert series, which will be just this power minus q. Okay, and what you can prove, because this is the sum side involves this multivariate independence polynomial. If you just work it out, then what you get as coefficient of this x power alpha is nothing but alpha multicoloring chromatic polynomial of G. Okay. So what is it? It is just defined in next slide. So what is alpha multicoloring? If you fix some q in n and then look at this alpha, which is summation k alpha I, then alpha multicoloring. So for each vertex, you assign multiple colors instead of one color. Okay. So the multiple colors, of course, they are coming from this given colors 1 to q. So you take this 2 power q, that is the power set of 1 to q. Okay. So each vertex, I am assigning multiple colors such a way that, so if you look at the vertex I, that should receive ki colors. Okay, because this ki is already given. And if you take any two adjacent vertices, they should receive completely disjoint colors. So those are all the properties. Okay. So the usual coloring, vertex coloring. So you assign each vertex one color and adjacent vertices should receive distinct colors. So here you assign each vertex I, ki colors, and then the adjacent vertices should receive disjoint colors. That's all. Okay. So then if you count this number of alpha multicoloring of G, then you can prove it is polynomial in Q, and you can have a very nice, very explicit description of that in terms of this independence of sets. Okay, that is indeed given in this identity. So this identity, you can take it as definition of this alpha multicoloring chromatic polynomial of G. Okay, so that's just obvious from the definitions. So now, so you can ask by doing this alpha multicoloring, are you getting anything new? Of course not. So the alpha multicoloring is actually connected with the usual chromatic polynomial, the usual vertex coloring. So the connection is given in this exercise. So if you start with alpha, and then what you can do, you can construct something called G of alpha. So what is that? That is the graph obtained from G as follows. For each I, you take a clique of size ki. So what is clique here? Again, so already you saw the definition of clique in the previous lecture. For me here, I'm taking it as a complete graph of size ki. Okay, but you can prove it will be actually maximal complete inside this graph that you are actually constructing. But anyway, this is just complete graph of size ki. And then what you do, you connect all the edges of ith clique and the jth clique, all the edges of jth clique, if there is an edge between I and j. Okay, it's kind of connected sum of those two copies. And then what will happen? Then if you take this G of alpha, which is which is the graph obtained this way, then if you look at this usual chromatic polynomial of that graph, that will be actually related to this alpha multicoloring of this G. Okay, this multicoloring chromatic polynomial. So this is easy to prove. So that means you are indeed actually not getting anything very interesting as in terms of polynomials. But still, these polynomials are interesting polynomials. Chromatic polynomials are very well studied, and we want to understand many properties of those polynomials. Okay, so let's move on. So as I promised, what one can do, like using this identity, so what you have here, so sorry, this identity. So this, once you raise it power q, then you are getting this multi-coloring chromatic polynomial here as coefficient of x power alpha. So then you can fix alpha and then compare the coefficients from the product side. Okay, this is sum side. So sum equal to product. So you can take the product and then raise it power q and then see how you can compare. By comparing that and then using some simple Mobius inversion formula, you can actually write down explicitly the formula for this dimension of G alpha. Okay, so the formula is given very explicitly in terms of this chromatic polynomials. Okay, so the dimension of G alpha is given by summation this mu of L divided by L, where mu is the Mobius function, and here this absolute value of the coefficient of q in this pi alpha G of q. Okay, you take that coefficient, so that's what appears. So if you can compute all these chromatic polynomials, then you will be able to compute what is the dimension of G alpha. So that's what this entire analysis tells you. Okay, and for many interesting families, one can easily compute these chromatic polynomials. That is not very hard. For example, if you take a complete graph, then you can very explicitly compute what it is. Okay, so if you take complete graph, what you get is actually free Lie algebra. It's called it's a free Lie algebra because you are not going modulo any relations, and this formula that is you have already that is already known formula. It's called Witt's formula. So Witt's formula gives you the dimension of G alpha. Okay, and of course this is also somewhat these numbers, this multiplicity of G alpha, they have very nice combinatorial natures. Okay, they count some very interesting numbers, and in the free Lie algebra case itself, they are very interesting. Okay, but in general, you can see already what they are counting on the right side. Okay, so they are very interesting things. And this coefficient of q inside this chromatic polynomial, again, they are very interesting coefficients, and they also have many interesting combinatorial interpretations. Okay, and if you do this tree with which has n vertices, then again one can construct this polynomial very explicitly. So that is given here. Okay, and using that again one can have Witt's formula, similar Witt's formula for trees. And now our procedure actually tells you that you can get it for any graph, not necessarily for for this special graphs. Okay, and of course this chromatic polynomial computed for many interesting families. So that is one application from like Lie algebra point of view, because if you start with this partially commutative Lie algebra, just staring at it will not give you anything. Okay, but computing this chromatic polynomial is very easy for many interesting families. From that one can actually get the information about the dimension of G alpha, and we use this information in one of our paper in Journal of Algebra. So that's I wrote that paper with Denis Kus and Arun Kumar, and using this information we constructed a nice basis of this Lie algebras LG. Okay, so that is one of the application. So let's move on.
Venkatesh, your time is almost up. Maybe you can wind up in a couple of minutes.
Oh, I'm almost done. Okay. Okay, so what I wanted to say is something related to this matching polynomial. So if you start with this matching polynomial mu of gx, so then this Godzilla actually constructed a rooted tree t comma r such that this kind of identity holds. Okay, so this G minus U is just graph obtained from G by removing this vertex U. Then similarly this is there. So you have such identity. Okay, that is somewhat easy to prove. It's not very difficult to prove. But what this identity tells you that if you rewrite, okay, I will not go to this construction. If you rewrite this identity, this ratio is same as this ratio. So by induction, you know that this mu gx actually divides this mu of tx. So as Apurva asked this, if you take this mu of tx, where t is tree, then this is actually given by characteristic polynomial of the adjacent matrix. So, but characteristic polynomials are well understood. They are real rooted. So that will tell you that this mu of gx is actually real rooted. Okay, so this actually motivates one to study this kind of identities. So what Banks actually did in 2018. So he actually generalized that for any independence polynomial. So of course, one variable independence polynomial. So he constructed given G, he constructed T dash such that the same identity holds. Okay, of course, one can generalize this identity easily for multivariate polynomial. There is no issue. Okay, what I'm interested in that multivariate version. So if you look at this multivariate version, so what happens, the left-hand side, it's easily seen that this is actually character of some highest weight representation of this LG. Okay, so then one can ask this question, whether this identity can be viewed as identity that comes from the isomorphism of representations of LG. Okay, so this is what I proved with Karthik Singh. The answer to this question is affirmative. So the answer is yes. Of course, one can construct action of that Lie algebra LG on this whatever model that we are having on the right side. Okay, so that can be given very explicitly. So we have action here of LG, and then there is this natural highest weight representation on left hand side. So that actually makes it okay. So what's our theorem is actually the module that we construct in this both ways will be isomorphic as LG modules. And using that isomorphism, one can actually get this identity. Of course, this isomorphism tells you more than this identity. So you have a weight preserving map from two combinatorial sets such that, and you will understand even graded wise. Okay. So it's much more than what you see here. So this is simple combinatorial identity, which can be proved very easily. It's not that difficult. But what we have is like very strong representation theory motive, like background for this identity, which is not that easy, but we managed to do that. Okay. Okay, I'll skip all this. I'll stop here.
Thank you, Venkatesh, for a nice talk. Any quick questions?
So what was it about real rootedness over here in this setting, or for general independence?
So the real rootedness actually, see, this is the thing here. So if you look at this identity, okay, maybe the one variable identity. So you need to understand the independence polynomial of this T dash.
Okay.
Okay. So because that the independence polynomial of the tree is not that easy to understand. So what Banks did actually, he constructed some interesting families of trees, okay, which has that real rootedness property, and he used that.
What is the real rootedness? Sorry, what is the real rootedness property? Just to be clear.
Real rootedness of this independence polynomial.
Okay, that's the family of graphs. Every polynomial is real rooted.
Yeah, exactly. Yeah. So why we are interested in real rootedness? That is because of that real rootedness gives log concavity, and that gives unimodality and so on.
Exactly. Right.
So that is why we are interested in. But here the drawback with the Banks idea is that one is relating this independence polynomial with this independence polynomial of the tree, but that is not well understood. So there is a very famous conjecture of Stanley that says if you take independence polynomial of this tree, the coefficient, absolute values of that coefficient will be unimodal. And yeah, that's not that easy to prove. It's still open. But Banks' motivation is just, okay, you start with some families which already has this real rootedness property. From that, he constructed many other families.
And these independent polynomials don't have some kind of determinant representation in general.
No. So yeah. So if they are actually, I know only for that matching polynomial. So which is for the tree it is true. Class-free independence polynomial again that can be handled somewhat. So this identity, for example, will give you real returns property for the class-free graphs. So again, same proof will work. Godzel proof. You can use induction and then this. To start with the class-free graph, then T dash will be class-free. That one can prove. And G minus U will be class-free. So again, induction will do that job.
All right, so if there are no more questions, let's give an applause to the speakers virtually. So, or over audio. Okay, so the next speaker is Teja. So we'll start the talk in